We are now going to look at the voltage, the potential, due to a point particle, and we are going to start down here with our equation for the electric field due to the point particle. So we know the electric field due to the point particle is given by kq on r squared. And just to remind you where that came from, we have the source charge, which is our point charge q. Our test charge q naught is in space, so any charge q naught that is put into space, F divided by q naught, the q naughts will cancel out, and we have kq on r squared as our electric field value. So that means we have all of these electric field lines pointing radially out, dropping off in strength as 1 on r squared. Well, we know our relationship between electric field and voltage is that delta V equals negative the integral E dot ds. We have to use the integral in the calculus. We can't just use ed because our electric field value is not constant. It's a function of r, so we plug that in for the electric field value. Our convention, whenever we are calculating a change in voltage, this is important, is to work inward from infinity. So if we are not told to bring in a negative charge, we will always use positive charges, bring them in from infinity. So our ds is going to be inward. Remember, our ds vector has a magnitude ds, but when we convert the ds to polar coordinates, that's where the extra negative comes, not from direction, from converting ds to polar coordinates, negative dr. So we get that extra negative in there. We have our cosine of 180, of course. So our two negatives give us a positive. And we have another negative. So that's where this negative is this negative. Here we have to be careful with our negatives. When we integrate 1 on r squared, I haven't shown all my integral steps here. Hopefully you can see that the integral of r to the minus 2 dr gives us integrate increase, r to the minus 1 over minus 1, so we get another negative 1 in there. So these two negatives, and the negatives are a little bit to track, these two negatives give us the positive that we have here. We have final minus initial, so we lose our 1 on infinity term. And we get our voltage. Of course, the reference is always arbitrary. We will reference the voltage equals 0 at r equals infinity to get V as a function of r equal to negative kq on r. And that voltage reference also makes sense based on our mathematical expression because when we plug in infinity for r, right, we get a voltage value of 0, so we are consistent. Delta V, don't forget about that. Delta V is always final minus initial. So we lose the initial here by our choice of reference, and we will be plugging in the positive and negative for the Q's in our voltage equations. And again, this gives us our individual voltage values. It is always delta V that we will calculate that has the physical meaning. So calculate delta V for individual problems. And that is it. This derivation would be a possibility that you would have to be able to work through and know, so please make sure you ask any questions about being able to derive the expression for the voltage function for a point particle.